Have you ever found yourself just, staring at a really complex bug, maybe a segmentation fault or a crash that just makes no sense,
Hmm.
or, and this is the classic one, code that runs perfectly fine on your machine but then just crawls on the server? You start to realize that the solution isn't in your syntax. It's deeper. It's in the architecture underneath it all.
Right. And that's the core of it. Writing truly efficient, high performance, and maybe most importantly, secure code, it all comes down to one thing. You have to understand how your program actually uses the hardware, how it organizes its whole thought process.
We call that organization the memory map.
We do. And I think too often we just treat RAM like it's this one big, simple swimming pool of memory. But the people who really know, the ones writing the operating systems and the compilers, they know that memory space is meticulously segmented. Every single slice has a very, very specific job.
So today, we're giving you that shortcut. We're going to dive deep right under the surface of the software and into, well, the digital brain itself. We'll quickly set the stage, connect the hardware to the software, and then we're going right into the nucleus. The 5 essential memory segments: text, data, BSS, heap, and stack that govern programs in languages like C or C++.
This is where optimization really happens.
Okay, let's unpack this. We're going to skip the elementary school lesson on what a CPU is,
Or RAM.
or RAM, right? You already know they're the brain and the immediate workspace.
Right.
But there's a concept that often gets overlooked,
Yeah.
and it's absolutely critical for performance and, well, for security. And that concept is virtual memory.
That's the key. That is the pivot point. It's not enough to just know that RAM exists. You have to know how the operating system, the OS, manages it. Virtual memory is what lets every single running program believe it has its own massive contiguous block of memory all to itself.
Even if the physical RAM is actually, fragmented or being shared by dozens of other apps,
Exactly. So if you're running 3 instances of your own application,
the OS makes sure they don't step on each other's toes.
precisely. The OS is like a really sophisticated bouncer. It translates your program's virtual addresses into real physical RAM addresses. And this whole system relies heavily on the bus, that's the communication highway inside the computer, and of course on cache memory.
This super fast temporary storage that kind of anticipates what the CPU needs next.
It smooths out that massive speed difference between the CPU and the main RAM. It's essential.
And that brings us right to the software. The OS is the ultimate arbiter here. We're not just talking about your application software.
No, not at all. It's the system software that really matters for this. The OS kernel, device drivers, even the firmware that's baked right into the hardware, all of that is responsible for defining these memory boundaries and protecting the SysD's integrity.
And those boundaries, they lead us directly to the memory map itself.
Correct. When a computer allocates memory for your program, for a running process, it doesn't just dump it anywhere. Main memory is instantly split into 2 massive segregated regions.
And this is that fundamental split, right? The kernel space and the user space.
That's right. Kernel space is reserved for the core of the operating system. All the drivers, the low-level stuff, it's critical infrastructure, and it's usually loaded in the lower memory addresses.
And it's highly protected, I assume.
Extremely. Your application cannot, under any normal circumstances, directly access or modify data in the kernel space.
So what's stopping my app from accidentally or maliciously crashing the entire operating system?
That boundary, it's enforced by the CPU's own hardware protection mechanisms, working with the OS and that virtual memory layer. Your application lives entirely within the user space, which is up in the higher memory addresses.
So if my app throws a segfault.
It usually just crashes inside its own little sandbox, inside its own user space memory. The kernel can then just gracefully terminate it without bringing down the whole machine.
So the user space, that's our domain. And that space, for something like a C or C++ application, isn't just one big blob. It's, as you said, segmented.
It is. It's a very specific organization, and the segments are laid out sequentially in memory. From the lowest address moving up to the highest, you have the text segment, then the data segment, BSS, the heap, and finally, way up at the top, the stack segment.
And that specific order is really important for how the program works.
Crucial.
I also just want to make a quick note here. Things like your command line arguments, environment variables, all those strings you pass to your program when you launch it, they're stored way up the top near the base of the stack. They're a part of the setup.
Now, if you're a programmer and you're focused on performance or debugging or security, 90% of the time you're focused on 2 of these, the heap and the stack.
The dynamic duo.
That's a good name for them because they are the 2 segments that are constantly changing size and storing almost all of your runtime data.
Okay, let's start with the stack. It's often called the program's scratch pad, what makes it so fast, but also so volatile.
It's all about speed and structure. The stack is where you store function parameters, local variables, return addresses, and it operates on a last-in, first-out structure, a LIFO structure.
Like a stack of pleats, you only ever add to the top or take from the top.
Perfect analogy. When a function is called, a little bundle of information called a stack frame gets pushed onto the stack. When the function is done, that frame gets popped off.
And that structure is what makes it so fast. The CPU can often just keep the most recent data in its own super fast internal registers instead of having to go all the way out to slower RAM.
Precisely. Now here's the key architectural insight. The stack is located at the very high end of the memory map, and it grows downward.
From higher memory addresses toward lower memory addresses.
Correct. It's usually the smallest of the segments, and because the system handles all that pushing and popping automatically, it's incredibly fast.
But that automatic process, that speed, is also what leads to one of the most famous problems in all of computer science, the stack overflow.
It's the classic risk. It happens when you try to use more memory than the stack has available. The textbook example is infinite recursion, a function just calling itself over and over and over with no way out.
So the stack just grows down and down and down.
Until it smashes right into whatever segment is below it, which is usually the heap, and then crash.
And the security side of this is actually terrifying. The stack buffer overflow attack.
Yes. This is a critical risk to understand. If your program uses an unsafe function to copy some data onto the stack, and that data is bigger than the buffer you allocated for it, the extra data just spills over into adjacent memory.
And what's in that adjacent memory?
Crucially, that's often where the return address is stored, the instruction that tells the CPU where to go next.
Oh, wow.
So if an attacker can overwrite that address with the location of their own malicious code, they can completely hijack the program's execution.
That makes the fragility of the stack incredibly clear. Okay, let's pivot to its big brother, the heap.
The flexible, sometimes messy big brother.
Right.
The heap is where you put data that needs to live longer than a single function call, or data whose size you don't know until runtime. We're talking about dynamically allocated variables, the things you use pointers for, with malloc in C or new in C++libs.
And if the stack grows down, I'm guessing the heap does the opposite.
It does the reverse, exactly. The heap is lower in the memory map, and it grows up from lower addresses toward higher addresses. It's almost always much, much larger than the stack.
But that power, that flexibility, it comes with a huge cost, responsibility.
The biggest headache for developers, frankly. Unlike the stack, which cleans itself up automatically, you have to manage the heap manually. If you call malloc or new to get some memory, you must remember to call free or delete when you're done with it.
And if you forget,
You get a memory leak. That memory becomes unreachable, but it's still marked as used. Over time, those little leaks add up, and they drain your system's resources until you get a heap overflow. You just run out of space.
the heap also has another problem that the nice, orderly stack avoids, which is fragmentation.
That's an excellent point. Because you're allocating and deallocating blocks of memory all over the place. At random, you end up with all these little holes. You might have, say, 100 megabytes of free memory in total. But if it's all chopped up into tiny 1 megabyte chunks and you need a 10 megabyte block.
Your allocation fails, even though you technically have the space.
Exactly. Your allocation fails.
Okay, so if the heap and stack handle all the dynamic runtime data, that leaves the static trio: text, data, and BSS. These are for the foundational parts of the program.
Right, the persistent parts. And they live at the absolute lowest memory addresses in the user space. Let's start at the very bottom, the text segment, sometimes called the code segment.
This one seems straightforward.
It's the easiest to define. This is simply where the compiled, machine-readable instructions of your program are loaded. It's your logic, your functions.
And it has a defining property that is absolutely critical for security and for modern OS design. It's typically read-only. Why is that so important?
Two big reasons. First, security. It stops a running program from accidentally or maliciously modifying its own instructions. That's a common attack vector. And second, efficiency. By marking the code as read-only, the OS can use shared code pages. Meaning if you have 100 users all running the same command, the OS only needs to load that text segment into physical memory one time. It then just maps that single copy into the virtual address space of all 100 of those running instances.
That's a huge resource saving.
Massive.
A great insight into optimization that goes way beyond just writing your own code.
Oh, yeah.
Moving up from text, we hit the data segment.
Also called the initialized data segment. This is where your global and static variables live, but only if they have been explicitly initialized with a non-zero value when you compiled the code.
So if I have a global integer, int counter equals 50, that 50 is stored here.
That value, 50, is stored in the data segment. Yeah.
Yes. And there's a careful distinction to make here because the data in this segment has a cost before the program even runs.
It does. Since these variables have initial values, those values have to be stored somewhere. They're stored inside the executable file on your disk. So the size of your data segment directly adds to the size of your program's executable file.
Which brings us to its confusingly named cousin, the BSS segment. Block started by symbol. This is for the uninitialized data.
Right. The BSS segment stores global and static variables that are either uninitialized or that you explicitly set to 0. And here's the really clever part of the BSS segment. The space for these variables is not stored in the executable file on disk.
So the executable file itself ends up being smaller because of this segment.
Exactly. The BSS segment just makes a note in the executable saying, hey, I'm going to need this much space for a variable named X. Then when the program is loaded into RAM, the OS just allocates that memory and fills the whole block with zeros.
It's a linking and loading optimization.
A crucial one, especially for programs that have huge global arrays that just start out empty. If that was in the data segment, it would just bloat your executable file for no reason.
So to clarify, both data and BSS store persistent global data. But the data segment is for the prepackaged information that adds to file size, and BSS is for the empty containers that only need space in RAM at runtime. That's a fantastic clarification.
Wow, okay. We just traced the entire architectural path all the way from the CPU's little scratch pad to the fundamental memory segments of a running program. We covered virtual memory, the protected split between kernel and user space, and then the full map.
The read-only text, the file-loaded data, the space-saving BSS, the developer-managed heap, and the fast LIFO-structured stack.
Yeah.
I think the biggest takeaway for you here is that now you know the real relationship between a variable's scope, its lifetime, and its performance. A local variable on the stack. It's fast, but it's ephemeral. An object on the heap is flexible, but it's slower, and you risk memory leaks. And a global in the data segment is persistent, but it's going to cost you disk space.
Knowing this, I mean, this is truly the difference between being a coder and being a software engineer.
And for those of you who want to actually see this in action, the source materials are spot on. You should use your system tools. On Linux or Mac OS, you can just use the size command on any compiled executable. It will literally show you the size of the text, data, and BSS segments.
And you can watch how changing your global variables directly affects those numbers. It's a really tangible demonstration of this whole memory map.
It really is.
Let me just leave you with one final thought, a provocative one, that ties this all back to that architectural design. If the stack lives way up in high memory and grows down, and the heap lives lower down and grows up, what does that deliberate opposing arrangement tell you about the fundamental goal of resource management inside a running program?
It tells you that the architects were trying to maximize the available space between them, giving both of those volatile data structures the biggest possible runway to grow without them immediately colliding. It's a constant, silent battle for every single byte. And that's something worth keeping in mind on your next coding project. Thanks for taking the deep dive with us.